It's funny. You look at something like a simple fan, and you just think, okay, it spins, it blows air, big deal, right? Well, it turns out that simple object is absolutely packed with incredible engineering and some seriously complex physics. So today, we're going to pull back the curtain and uncover the hidden science of fan design. So I'm sure you've seen this. You're shopping for a fan, maybe for your PC, your bathroom, whatever, and you see this number on the box, 120 CFM, and you're just kind of supposed to know what that means. But what is it really? And more importantly, how do engineers even come up with that number in the first place? Okay, so the letters stand for cubic feet per minute. It's basically a measurement of how much air it moves. But here's the thing. That number isn't just a simple stat. It's not just about raw power. It's actually the result of this hidden, invisible battle that's happening every single second that fan is running. And this battle? It's being fought between aerodynamic lift, some really complex physics, and the very air in your room. Yeah, we're talking about the same principles that let a jumbo jet get off the ground. It's a whole story of physics and engineering. So let's dive in and start from the beginning. All right, so how do fans actually work? Well, it all comes down to two basic moves. Seriously, every fan you have ever seen, whether it's a tiny little thing cooling your computer or a massive industrial blower, uses one of just two fundamental methods to get the job done. So the first way is what's called the centrifugal effect. The easiest way to think about this is just slinging. The fan grabs air from the center and literally flings it outward. The other way, that's aerodynamic lift. This one is all about pushing. The blades are basically little spinning airplane wings that create a pressure difference and just push the air straight forward. And those two basic ideas, slinging versus pushing, are exactly why fans look so different. The job the fan needs to do determines which method an engineer picks, and that leads us to a tale of, well, three wheels in a wing. Okay, let's start with those centrifugal or slinging fans. They kind of look like hamster wheels, right? Well, just by changing how the blades curve, you get completely different results. You've got forward curved blades. They move a ton of air, but they're not very efficient. Then there are radial blades. These guys are tough. They create a ton of pressure, which is perfect for industrial stuff, like sucking up sawdust. And finally, the backward inclined blades. These are the undisputed champions of efficiency. That's why you'll find them in all the best high-end HVAC systems. Now let's talk about that spinning wing, the fan you're probably most familiar with. It's pure aerodynamics. So a few things are absolutely key here. First, the stagger angle. That's just the tilt of the blade. A high tilt gives you lots of airflow. A low tilt gives you high pressure. Then there's solidity. Basically how wide and how close together the blades are. More solid means more power. And here's a super cool detail. The blades are always twisted. Why? Because the tip of the blade is moving way faster than the part near the center hub. That twist makes sure the whole blade is working perfectly in sync. So, okay, engineers know all these principles. But how do they actually go about perfecting a design? I mean, they don't just build hundreds of physical prototypes anymore. No way. Today, it's all about this incredibly powerful digital toolkit they use to design, test, and totally optimize a fan, all before a single piece of metal ever gets cut. But before we get into the tools, you have to understand the stakes. And this quote right here says it all. A user might request just 10% more airflow. The result can be a 33% spike in power consumption. Whoa. This is all because of something called the fan affinity laws, and they show how a tiny little change can have massive, and I mean massive, consequences. Let me show you what I mean. So let's start with a simple request. Your boss says, hey, we need just 10% more airflow. Okay, easy enough, right? The simplest way to do that is to just spin the fan 10% faster. No big deal. Or so you'd think. But this is where the physics just jumps in and bites you. Those fan laws say that pressure doesn't just go up by 10%. Nope, it goes up by the square of the speed change. So that little 10% speed boost just caused a 21% spike in pressure. And here it is, the real kicker. Power. Power scales with the cube of the speed. That simple 10% increase in airflow now demands a staggering 33% more power from the motor. And if that motor wasn't designed to handle that extra load, poof, it overloads and burns out. This is why those digital tools are so absolutely critical. That main tool is called computational fluid dynamics, or CFD for short. You can pretty much just think of it as the virtual wind tunnel on a supercomputer. So what engineers do is they create a perfect 3D model of the fan. Then they break up the air all around it into millions of tiny little cells. From there, they let the supercomputers solve all the crazy equations of fluid flow for every single one of those cells. This lets them literally see invisible problems, like little whirlpools of air, vortices that waste energy. And they can fix it all in the computer, long before they build anything real. Okay, so now that we're armed with all this knowledge about the physics, the different shapes, and the modern design tools, let's circle all the way back to that original question. What does that number on the box, that CFM reading, really mean? It's time to finally solve this mystery. But wait, first things first, is it CMF or CMF? You'll see CMF written down sometimes, but honestly, in the world of fans and ventilation, that's pretty much always a typo. The term you're looking for is CFM with a CFM. All right, so CFM, as we said, is cubic feet per minute. A good way to think of it is like the aerodynamic currency for ventilation. It's the unit of measurement for how much air needs to move. But here is the single most important thing to understand. That CFM number on the box, it's not a fixed value. A fan doesn't just produce 120 CFM all the time, no matter what. The actual CFM a fan gives you is the result of that battle we mentioned at the very beginning. It's the exact point where the fan's power curve meets the system's resistance curve. And what's resistance? Well, it's anything that gets in the way. Ducts, vents, grills, and especially air filters. You know how your AC doesn't work as well when the filter's clogged? That's because the resistance is way higher, so the fan is delivering a lot less CFM. And just to be thorough while we're on the topic, if you do see CMF used correctly, it probably means one of two other things. In industrial design, it's color, material, and finish. Stuff that affects how durable or easy to clean something is. Or in some super specialized science and engineering fields, it can stand for Coriolis mass flow, which is a really, really precise way of measuring gas. So there you have it. That number on the box isn't just about power at all. It represents this perfectly engineered balance point, a kind of truce in the ongoing battle between the fan, the system it's placed in, and the fundamental laws of physics. Kind of makes you wonder, right? What other everyday object are you going to look at differently now?